In this lesson, we are going to review solving various types of inequalities, such as linear inequality, polynomial inequalities, rational inequalities, and absolute value inequalities. When we solve system of inequalities, quite often we are interested in union of solutions. So let's review what's a union of two sets. If we have a set A and a set B, then the union of these two sets consists of all the points that belong to set A or set B. That means everything what's in both of these bubbles. Formally, union of a set A and B is marked by using the sign U, and it represents all the points X such that X either belongs to A or belongs to B. We also need to recall the concept of intersection or product of two sets. The intersection of two sets is marked by the upside down cup, like this, and it represents the common part between set A and B. So the common part is the overlapping part, all the points that belong to both sets A and B. That's why the connecting word in the formal description is and. The intersection of the two sets A and B are all points X such that X belongs to A and at the same time X belongs to B. So the connecting word that indicates intersection of two sets is and the connecting word that indicates union of two sets is or. Quite often people have problem to remember which way this cup will go, either the regular cup or upside down cup. Well, I remember it that way. If you write the word or, and if you write it a bit sloppy, the R becomes like this U. And when you write the word and, the middle N looks like the sign of intersection, upside down cup. So how do we solve inequalities? Well, basically we solve them the same way as equations, except for one moment. When we multiply or divide by a negative number, then we have to reverse the inequality sign into opposite. So here we have the first example. Solve, graph, and state your answer in interval notation. When solving inequalities, remember to state your answer in interval notation, even if the instruction is not there. So how would we approach this inequality? What would be the first step to solve it? I would suggest to put together the 6 and 8, bring it to the other side, but sooner or later also multiply by 3, so you will get rid of this fraction. Okay, let's multiply by 3, and in the meantime add 6 to the other side. When you multiply by 3, 1/3 will be gone, so you really have just a bracket, 2x plus 5. Then the 6 will be gone to the other side. 5x needs to be multiplied by 3, making it 15x. And when I add 6 here, then I have really -2, and this -2 will be multiplied by 3, so it's -6. Now put all the x's to one side. We could do it to the left, but then we'll have a negative number of x's. So it's probably easier to bring the 2x to the right-hand side. So 15x minus 2x is 13x. 5 plus 6 is 11. And finally, the x is smaller equal than 11/13. Notice that if I would bring the x's to the left at that stage, I would get -13x bigger equal -11. And then I will have to divide by a -13, which causes switching inequality into opposite sign. So inequality will be like that. So -11 over -13 is still 11/13, and as you see, the answer is exactly the same as before, however it's written from different end. So here you rate this from the left to the right, x is smaller equal than 11/13. Over there you rate the inequality from the right to the left, and again x is smaller equal 11/13. So now we can draw it on the number line. If this is my number line and somewhere there is my 11/13, then x's that are smaller or equal are actually over here. And that's the set of all possible x's that are smaller equal than 11, 13. Now we're ready to give the final answer, which is x is an element of the interval from minus infinity up to 11, 13 inclusive. Here we have a couple examples of compound inequalities, either with the connecting word or the simultaneous inequalities that are really with the connecting word and. Let's start with the or case. We solve one inequality. 2x is smaller equal 3 plus 5 is 8, therefore x is smaller equal 4. Keep writing the connecting word or and solve the other inequality. 3x is bigger than 15, meaning x is bigger than 5. So we have x smaller equal 4 or x bigger than 5. Let's draw it on the number line. If I have equation, I should use covered dot, meaning with the endpoint, so that will be my 4. X's are smaller than 4, that means this way. And here we don't have any equal sign, so we use the hollow circle, and x's are bigger than 5 if this is 5, so the x's are over here. Because the connecting word is or, then we are taking union of these two sets. That's a union. Therefore, the final answer is x belongs to from minus infinity. You always read from the left to the right. So you start with minus infinity, comma up to 4 inclusive, then union from 5, round bracket, no endpoint, up to infinity. The example B should be considered as two inequalities, two simultaneous inequalities, this one and that one, that needs to be satisfied by the same x. So the connecting word between these two inequalities is and. You can rewrite them separately, but it's actually a lot easier to work with them just as they are written, with 3 sides. So what we do, we want to solve for x, therefore we want to get rid of 4. We're going to multiply both inequalities by 4. So we apply this multiplication by 4 to all 3 sides of the compound inequality. So -1 times 4 is -4. This fraction, the 4 will disappear, so you have just 2x plus 5. And here 3 times 4 is 12. Next, to be closer to x, we want to get rid of 5. So we're subtracting 5 from all 3 sides, the same way as when solving equation and applying certain operation to 2 sides. Now you apply the same operation to all 3 sides. So -4 minus 5 is -9. Here the 5 disappears because it's subtracted, and over there is 7. Finally, we need to divide by 2. So let's divide by 2. So it's -9 halves x and 7 halves. So we can see that the solution set, when marked on the number line, this will be point -9 halves, and that one 7 halves. The x must be larger than -9 halves, but at the same time smaller than 7 halves. So the overall common part is between -9 halves and 7 halves. We can think about x as oscillating between these two numbers. So all those numbers can be taken and they will satisfy both inequalities. Therefore, our final answer is x can be any element from the interval from -9 halves up to 7 halves. Square bracket. So this is the standard picture for the situation with or. Most often, your answer will look somehow like this, with 2 branches. For the inequalities with connecting word and, we'll expect just one segment, the common part of the 2 solutions. However, we may have some exceptions. Let's see what will happen in this example. The first inequality, as you see, is exactly the same as in example A. So when you solve this inequality, you end up with x smaller equal 4. The second inequality is tiny bit different, so let's solve it. 3x is bigger than 6. Divide by 3, therefore x is bigger than 2. So what we have is x is smaller equal than 4 and bigger than 2. Let's graph it on the number line. When you mark your numbers on the number line, remember that the smaller number is positioned more to the left than the larger one. So the 2 would be here and open circle because we don't have equation here, and the 4 would be over there with the covered circle because of the equation. Now x is smaller or equal than 4, so the interval goes this way. Or x is larger than 2. Larger than 2 means that way. Well, normally you would think of taking intersection, but we actually need to look at this connecting word or. So remember to check what is the connection between the two inequalities. Or means take union of these two sets. So everything what's here or there, which means the entire number line. So in this case, the answer would be all real numbers. Any chosen real number will satisfy either the first inequality or the second inequality. Well, let's look at the last example. Here we have x is smaller equal 5 and bring the x to the right, so x is smaller, then bring the 1 to the left, 3. Again, see how this will look on the number line. 3 is below 5, so 3 will be hollow circle, the 5 will have to be covered circle because with the equation x is smaller than 5, meaning it goes this way, and x is smaller than 3, so this set also goes that way. Now the connecting word is and. And means take intersection of these two sets. Common part, the overlapping part. Well, the overlapping part is just this one. So ready to give the final answer. Read from the diagram, starting from the left. X can be any element from negative infinity up to 3. So these two last examples shows you that you really need to watch the connecting word and make sense of the union or intersection rather than stick with the pattern that maybe happens very often but not always. Here we are going to observe how to solve absolute value inequalities. If we have absolute value of something, some unknown expression, that is smaller than a certain constant number k, then to solve such inequality, we need to drop the absolute value first. To drop this absolute value, think about geometrical interpretation of such inequality. Your expression is smaller than k steps from 0. So if I have a number line and somewhere there is 0, I can go k steps one way or k steps the other way, and the expression by itself, expression, not x, is in between negative k and k. So it's kind of inside the circle with radius k. Therefore, to drop the absolute value, we rewrite the same expression and then close it by negative k and k as stated here. And then solve it. If you don't have absolute value, this will involve some sort of variable, usually x, and then you solve the standard way like we showed in the previous slide. The other case is when the absolute value of something is actually larger than k. So look on the number line. If this is 0, absolute value of expression means that the expression by itself is farther from 0 than k steps. So it's at least k steps or more to the right, or at least k steps or more to the left, farther from the center. So if you think about circle of radius k, this set will be outside of the circle of radius k. So to drop the absolute value, we need to rewrite this in two inequalities connecting by the word or. Either the expression is to the left of negative k, so it's smaller than negative k, or the expression is to the right of k, so it's larger than k. So again, to drop the absolute value, we rewrite the expression into inequalities, like this, connecting with the word or, and solve them separately and then make sense of the final answer using the union of these two solutions. Let's see how it works in practice. First inequality, we have something in absolute value smaller or equal 5. Therefore, this something should be enclosed by -5 and 5. So the connecting word between these two separate inequalities is and. So let's solve it for x. We are going to subtract 1 first. So this will be -6 smaller or equal -2x smaller or equal 4. Then we wish to get rid of -2, so let's divide by -2. Remember, when you divide by a negative number, red alert, we're going to switch inequalities into opposite. So -6 divided by -2 is 3. This -2 will be gone, so it's just x. And 4 by -2 is -2. As you see, we have very nice final answer. X is really in between -2 and 3. It oscillates between -2 and 3. We can draw it on the number line. -2 is more to the left, so let's say it's here with closed circle. And 3 again with closed circle is there. X is larger than this number, but smaller than that number. So it's everything what's in between. And let's give the final answer. Therefore, x can be any number from -2 to 3 with square brackets. Okay, and the following example, here we have absolute value of some expression is farther from 0 than 1. That means that my expression is either below -1 or the same expression above 1. This is very important that you rewrite it in a proper way. Don't try to solve equation. You have to actually solve inequality. So keep in mind these two rules that I gave you. Okay, let's follow up. Solve this one. That will be 4x smaller than -1 plus 3 is 2. Therefore, x is smaller than 1/2. Or 4x is bigger than 4. Therefore, x is bigger than 1. And again, let's draw it on the number line. X is smaller than 1/2. Let's say 1/2 is here and all x's smaller are there. Or x is larger than 1. So let's 1 will be here and all the numbers larger over there. We are talking about union because of the connecting word or. So we are going to use union. Therefore, the final answer is my x can be anything from, starting from the left, -infinity up to 1/2, round bracket, union, or from 1 to infinity. Now let's recall how do we solve polynomial inequalities. For example, something like this. Well, the first step would be to make sure that we have entire polynomial on one side and make the other side equal to 0. So we're going to bring everything to one side. X cubed minus 3x squared minus 10x bigger equals 0. That's the first step. Then we are going to factor completely the polynomial that we've got. So how do we factor this particular one? Well, we have x as a common factor, and then we have x squared minus 3x minus 10 bigger equals 0. Is this polynomial factorable? Product 10, difference 3. Well, that's possible. Should be -5 and 2. So let's factor more. Factor completely. X minus 5 and x plus 2 would work. Bigger equals 0. So we've done this point. Now the next step will be find all critical values. What are critical values? Well, those are the values that will make any of those factors 0. So critical values are real zeros of the polynomial. So let's list our critical values are 0 from here, 5 from this bracket, -2 from that bracket. Okay, so we listed critical values. In the following step, we are going to analyze signs of all those factors. We are going to draw the number line, maybe somewhere here. List all the factors. So list x in one row, x minus 5 in the next row, and x plus 2 in the following row. So we're going to think of those expressions, how do they behave on the number line? And we're going to cut the number line by our critical numbers. So the lowest one is -2. This line will represent -2. Then it's 0. So let's say somewhere here it's 0. And somewhere there is 5. Those three numbers are cutting the whole domain of real numbers into 4 regions. And we are going to analyze how each of those expressions behave in each region determined by those critical numbers. So analyze signs of all factors in all critical intervals. That will be the next step. Let's do it. How x behave? Well, x changes its sign at 0. If x by itself is lower than 0, then we mark negative. If x is larger than 0, then the value of this expression is positive. Now x minus 5 changes its sign depending where the x is. If x is lower than 5, for example 4 or 0 or -1, then 4 minus 5 is negative. 0 minus 5 is negative. So in all those intervals below 5, the expression x minus 5 will be actually negative. The sign of this expression is positive when x by itself is larger than 5. For example, 6 minus 5 is positive. So the expression becomes positive in this whole interval. And finally, the third one, it changes its sign at -2. So if x is lower than -2, for example, -3, the value of it is negative. If it's larger than -2, for example, -1 or 0, this expression becomes already positive. So positive here, here, and there. Now, after the sign analysis, we are going to state the result. Since our polynomial is a product of those three factors, then we are really multiplying the signs in each interval. So 3 negatives becomes negative, 2 negatives makes it positive, 1 negative, negative, 3 positive, positive. So we know how the entire polynomial behaves itself on the number line. Okay, let's come back to the inequality. The inequality asks us when this whole polynomial is bigger equal 0. Well, it's definitely bigger than 0 here and over there because we see positive. We also need to check the endpoints of each interval. Since the equality is allowed, then we can actually take the endpoints. Therefore, endpoints will be marked by covered dot. And we are ready to give the final answer. The original inequality is satisfied by any x from the following intervals, from -2 to 0, union with interval from 5 to the infinity. All those points are good. We apply similar idea when solving rational inequalities. Using this example, I'm going to illustrate the above steps. When you deal with rational inequality, first of all, make sure that you have 0 on one side. So make one side equal 0, and the other side must be a single fraction, because we want to have either product or quotient of linear factors. If it's addition or subtraction, we won't be able to use zero product property. So a single fraction, put everything together under one division bar, that's important step. Okay, so the first step would be to move the 3 to the other side. smaller than 0, and then create a single fraction. That means put these two quantities under common denominator, x minus 4. So the numerator here is x minus 8, and then it's minus 3 times the denominator x minus 4, smaller than 0. Now we can simplify, so it's x minus 8 minus 3, 8 plus 12 over x minus 4, smaller than 0. And finally, maybe we'll write it here, we have negative 2x plus 4 over x minus 4, smaller than 0. At that moment, it's important to check if we can possibly factor numerator and denominator. We should factor completely each numerator and denominator. However, in our example, we have both numerator and denominator as linear polynomials, so there's no need to factor anything more. However, if we wish, we could divide the whole equation by negative 2, meaning that the inequality will reverse. So dividing by negative, switch the inequality. And this would give us a bit easier expression. It will be x minus 2 over x minus 4 bigger than 0. So since we divided by a negative number, the inequality changed. From now on, we are going to look at solving just this inequality, which is equivalent to the original inequality. At this moment, I want you to come back to the first step for a second, because quite often students decide to multiply the whole inequality by this denominator to the other side. I would advise you not to do it. And why? If you multiply by a negative number, you should change the inequality. But since you don't know if this is positive or negative, you will need to consider two different cases. When it's positive, when it's negative, how to change inequality. That quite often leads to some mistakes. So please don't multiply by denominator, but rather bring the 3 to the other side and keep one side equal to 0. Okay, so we have a single fraction on one side in a factored form and 0 on the other side. So again, we're going to use the 0 product. It's not a product, it's quotient, but it works the same way as products. So we analyze signs. The fraction is positive when both numerator and denominator have the same signs. So let's find out critical values, the same as before. Critical values are from the numerator is 2, from denominator is 4. That tells us how to draw signs on the number line. Well, first let's list our two expressions, x minus 2, one row, x minus 4, the other row, and the result at the bottom. And then mark the critical values on the number line. Somewhere here is 2, and 4 is somewhere there. And then we analyze signs. If x is smaller than 2, for example 1 or 0, this expression becomes negative, so we mark minus in this box. If x's are larger than 2, for example 3, 4, 5, this expression becomes positive, so let's mark those signs in proper segments of number line. Now x minus 4 changes its sign at 4. To the left of 4, it's easy to check, the expression is negative. To the right of 4, when x is, let's say, 5, the expression becomes positive. We rate our final result by combining the signs from each column. So 2 negatives becomes positive, that's negative, and this is positive. So now let's come back to the question. When the quotient is bigger than 0, we are asked about the segments where the result, that means the quotient, is positive. So it is positive here and there. We also need to check the endpoints. Since 4 is not in the domain of this expression, then 4 can't be taken. So it's an open circle. And we can make a record of it because 4 is not in domain. Now the second number if we would have the equation sign here, then it could be taken, because then the whole expression would be 0. But we don't have equal sign, so no equal sign, no point, no endpoint. Therefore, the final answer is these two intervals, and we can state it as follows. X is any number from -infinity up to 2 without 2, or from 4 to infinity. So again, review the steps. We did make one side equal to 0, and we make sure that we have single fraction on this side. We factored completely if needed. In this case, it wasn't really needed, but you may have higher degree polynomials and you may need to factor them. Then we found critical values, the zeros from numerator or denominator, 2 and 4 in this case. Finally, we divided the number line into the segments by using those critical values. And then we analyzed signs inside the table of signs. And at the end, we read the answers from the diagram and stated it in interval notation, watching the numbers that are not in domain. Always check against the domain of the original expression. Here we have one more example. This is a very special one, because looks like it's more difficult than previous, but it actually isn't, because if you look at the numerator, this is always positive. This numerator is always positive because of the square, right? So the sign of the overall expression really depends only of the denominator. So it's basically only one thing to check. So it's enough to solve the inequality 2x plus 1. We want to have it smaller than 0. Why not equal? Well, because we can't keep 0 in denominator. So no equation because of the domain. So strongly smaller than 0. Okay, then when we solve it, this becomes smaller than -1/2. Now we can mark this on the number line. Let's say -1/2 is here, and all numbers that are smaller than -1/2 will work because they will make the denominator negative and the numerator will be all the time positive, so the overall fraction will be really negative. We also need to watch the fact that the inequality contains equal sign. So when this fraction is equal to 0, well, it's equal to 0 when the numerator is 0. When 5x minus 3 is 0, well, when x is equal to 3/5. So that's also a point that will make this inequality true. Therefore, we need to include a point 3/5. So as you see, you really need to work like a detective. Check all the critical numbers, check the endpoints, what's going on, should we take them or not, and why. So check for the domain, check for the equal sign. From this diagram, we can state the final answer. X can be anything from -infinity up to -1/2, but also 3/5 can be taken. So it's a union of interval and a set composed of one element 3/5. Just for your own practice, please try to solve similar inequality, so the same expression 5x minus 3 squared over 2x plus 1, but larger than 0. So see if you can come up with a good answer for this one. And the last example is showing some application of inequalities. A shoe manufacturer finds that the monthly revenue R from a particular style of aerobic shoes is given by this formula, where P is the selling price of one pair of shoes. Find the price interval for which the monthly revenue is at least $5,925. So the monthly revenue is given by this expression. We can take it and we can compare it to $5,925. The monthly revenue should be at least means bigger or equal. So 312p minus 3p squared must be bigger or equal of 5925. This looks like a polynomial inequality. So if we bring everything to one side, we have 3p squared plus 312p minus 5,925 bigger equals 0. Let's divide everything by -3 because it's easy to check that these two numbers are divisible by 3 and we don't want to keep the negative in front. So let's divide by -3. We'll obtain p squared minus 104p plus 1975 smaller equals 0. Since these numbers are quite large, we could try to factor it, but we also could try to use calculator. So figure out how this polynomial, it is a parabola because it's a quadratic polynomial, how this parabola looks like and in what interval it is below 0. So we will expect a picture of it to be somehow like this. And for these two particular numbers, the value of this polynomial will be 0. So when this value is smaller than 0, well, between these numbers. So we're going to look for those numbers. There's two options. We can use calculator or we could use quadratic formula. Since I wish to introduce you to using graphing calculator, let's open a virtual calculator and we'll see how can we take advantage of the graphing calculator features. So on your calculator, please push the y equals button and just plug it in this polynomial as function using x instead of p. So we go x squared minus 104x plus 1975. So that will be our function. We want to graph it in a system of coordinates such that when p is 0, I should see this number. So I need to change the window. For example, start with x minimum from 0 up to, well, let's use 100, and y negative 1,000, and y maximum about 2,000. So that looks good. Here we have the graph. Now to find these 2 points, this and this intercept, we can go second calc, so second trace, which recalls the calc function, and we're going to calculate zeros, so push 2. You can do it by using arrows, highlight the 2 and enter. The calculator asks what is the left bound. The left bound of the first 0 that we wish for has to be set up before the 0, so from the left of 0. You can do that by using a right or left arrow. And then enter. Then right bound a little bit after the 0. And enter again. And they ask about guess. You can make it closer to the 0 or you can just enter again. And you have the 2 coordinates of the 0. X is 25 when y is 0. So this number will be actually 25. And let's do the same, second calc. Calculate 0 again, number 2 for the second 0. Scroll it closer to the second 0, but still from the left. Scroll it until we'll get nearly to the 0. Enter, and after the 0. This tells the calculator in which region the calculator should look for the 0, and enter again. So the second 0 is 79, and we can record this on our picture, 79. Okay, therefore we can give the final answer. Find the price interval for which the monthly revenue is at least 5,925. This price interval is from $25 up to $79 inclusive. So any price P that is between 25 and 79 inclusive the endpoints will result in revenue of at least $5,925.